Okay, so now we're carrying on from the previous lecture where we introduced covering spaces. And now I want to talk about some slightly more rich family of covering spaces. So what we start here is with this, this base space, which is sometimes called S1 wedge S1. And it is two circles put together at a point. Okay? So we're taking two circles and we're gluing them together at a point, and I'm calling that S1 wedge S1. Now, this space, in terms of its fundamental group, has two obvious generators. There is a loop alpha, say, we'll use this as the obvious base point. Maybe we should call it B. No, we'll call it X0. So there's one loop alpha going around this way, and another loop, say, beta, going around in this direction. And then by composing various powers of alpha and beta, we can get some rather sophisticated loops in this space. So pi of this space B is some kind of product, is a product of the infinite cyclic groups of the fundamental groups of the associated of each of the individual two circles. Is a product of the two cyclic infinite groups generated by alpha and beta. So for example, we have things like alpha squared, beta cubed, alpha inverse beta, for example. That would be the loop that goes like this, twice around this one, three times around this one, once in the opposite direction of alpha, and then once more beta. So it's a rather rich fundamental group. And we're interested in covering spaces of this base space B. So it turns out that covering spaces of this are rather rich and not so easy to understand, at least at first. So what are some examples of covering spaces? What are covering spaces of this space B? Well, one thing we could do is we could take the base space B, we'll sort of put it in a plane here, and we'll think about putting something on top of it. There's a kind of an obvious, easy construction that we can always do, which is almost trivial. We could, for example, take two copies of the base space and call this composite thing X. And we could just define the projection to be the obvious projection that sends each point here to the associated point down here. That would be a covering. It's a trivial kind of covering. Because X is really just the base space B cross the set 0, 1. The set 0, 1. Just two copies of B. So it's relatively uninteresting. To make something a little bit more interesting, we could do a variant. We could have our base space here. And we'll take these two copies of B that we had up here, and we'll modify things a little bit by, well, sort of thinking of a double covering, say, of one of these circles. So instead of having two circles covering this one, we'll make these two circles here a double cover, like a helical double cover. How could we do that? Well, we could sort of cut the circles, these ones, and glue this one to that one there, and glue this one, well, to that one there. Maybe it's not so easy to do. Maybe I'll just come straight down. So what we end up with is a sort of a helical situation for one of them, and the loop on the other. Now that's a little bit awkward to draw, so I'm going to draw it in a different way. I'm going to draw it rather as in the following way. So here's our base space, and we'll keep the notation alpha and beta. So let's draw another one that looks like this, beta, and then so what I'm doing is I'm taking this thing here and I'm kind of laying it out a little bit flat so we can see it better. And I'm using these labels so that every edge is still labeled alpha or beta. Okay. Now I have to describe what is the map, the projection from this space X to the base space B. And the rule is that we just look at any one edge that we're up here. Let's say we have a point X here. Well, it's on the beta edge. It's a certain ways along the beta edge. So we just go that same amount on the beta edge down here, and we declare that to be P of X. So for example, this one here, this point Y here, is maybe 5/6 of the way around alpha. So we go 5/6 of the way around alpha, where alpha goes all the way up here. So there would be P of Y. This point here, let's call it Z, it's also on an alpha edge. It's also 5/6 of the way roughly along the alpha edge. So it would also be mapped to this point here. So we're going to use the orientations of these edges to prescribe the covering. Well, once we've done that, then we can cover this base space B in a number of different ways. So other covers, for example, we do note this base point here by x0, then in both this example here, these 2 points here where we have 4 things coming together are both obviously going to have to get mapped to the x0 because that's the only point that has that special property. Here there are 2 such points that have that property, and they're also going to get sent to x0. Okay. So the mapping would be as follows. So this point here would get sent to this point here, and if we go trace down this path here, then this path would get mapped to this path beta down here. While this path beta going in this direction would also get mapped to that path beta down there. So the directions of the labels tell us what the map is. So we go down alpha in this direction. That means we're going to map to alpha all the way along down there, starting from here and ending up at the same point. This one here also gets sent to this thing here. So let's look at the covering properties. Suppose we have some point, let's say, call it B here, and let's look at the inverse image of B. This is maybe 1/3 of the way along alpha, so the inverse image would consist of the things that are 1/3 along alpha. There'd be one there and one there. So there'd be one point, say, C and C, C and C prime. So P of C and P of C prime are both that point B down there. And it's clear that a neighborhood of the inverse image consists of 2 copies of a neighborhood that looks just like the neighborhood of B down here. More interesting and more important to check is what happens to x0 and its inverse image. So the inverse image of x0 consists of both of these points. So if we choose some neighborhood of x0, which has 4 little arms coming in, then we see that here also we have 4 little arms coming in and 4 little arms coming in. And the nature of the edges coming in is the same as it is here. Here, locally at x0, we have 1 alpha coming out, 1 alpha sort of arm going out, and 1 alpha arm going in. 1 beta arm going out and 1 beta arm going in. Here the same story happens. We have 1 alpha arm going out, 1 alpha arm coming in at this point. 1 beta arm going out and 1 beta arm coming in at this point. Similarly at this point. So at each inverse image of x0, we have 4 edge, well, let's say edge arms meeting, an alpha in, an alpha out, a beta in, and a beta out. So if you're just in this neighborhood here, you can't tell whether you're in this graph or in this graph. They're the same. Locally, they look the same. Although globally, of course, it's quite different. As graphs, these are actually proper edges. Well, these are loop edges. Okay, so this is all what's required to get covering space of this B. All what we need is a map, a graph, that has this sort of property that the edges are all labeled alphas and betas, so that at every point where there's a vertex, we have 4 things coming in. 2 of them labeled alpha, 1 going in, 1 out, and 2 of them labeled beta, 1 going in and out. So here are some other covering spaces. Some more coverings of B. And let's just remind ourselves what B looks like. It's like this with an alpha and a beta. Now we're calling that edge x, that point x0. Okay, so all right, so here's another graph whose edges are labeled by alphas and betas. There are 3 vertices. At every vertex, if you look locally, you see 2 alpha edges, 1 coming in, 1 coming out, and 2 beta edges, 1 coming in and 1 coming out. Here's another one. This is an infinite graph, which has a string of beta edges all along this row. And associated at every vertex, there's a loop labeled alpha. This is another covering of the base space B. At every one of these vertices, we can check that we have 4 edges. 2 of them are betas, 1 going in, 1 going out. 2 of them are alphas, 1 going in and 1 going out. All right, so in all these cases, the map from this space X to this space B is just given by mapping the alpha and the beta loops either to this alpha or to this beta. As you go around this alpha here, that whole thing gets mapped 1-to-1 onto that loop there. As you go from here to here, you're mapping from here to here. It's a well-defined map from X to this base space B. Well, we can do, there's many different possibilities. Let me do one is particularly important one. Okay, so the most important covering in some sense. This is called the universal cover. The universal cover of B, and it has the property that it is simply connected. In other words, there are no non-trivial loops on it, i.e., no non-trivial loops. Or in other words, pi of x equals just the identity. That's not the case with these. These are certainly not simply connected because they have loops. There's a loop. That's a non-trivial loop. That's non-zero in the fundamental group. Here there's lots of non-trivial loops. There's a non-trivial loop. You can't homotopy it to the identity. So we're interested in a covering space for B which is simply connected, in which there are no paths that start and end at the same point, which are not essentially trivial paths. So how do we construct this covering space for this space B? Well, we basically follow our noses and do almost the only thing that we can. We just start and continue and carry on. So we know there's going to be at least one point x0, and let's say that, okay, there's got to be two alpha edges, say an alpha edge going out and an alpha edge coming in. And there's got to be two beta edges, say a beta edge coming in and a beta edge going out. Okay. Then there are going to be two or four more vertices, and they're also of the same kind of x0 of type. So they also have to have the same property, that there's got to be four edges coming into each one of these vertices. So at this vertex here, we also have to make sure that there's another beta edge going out. And I'm going to make this new beta edge a bit smaller. Okay? So the diagram is going to be a little bit curious. Because this is going to be a huge infinite graph. And if I make them all the same size, they will overlap enormously and we will not be able to see what's going on. So I'm going to distort the sizes of the edges so that I can fit them on somewhat reasonably on this page. So this beta is going to be a little bit smaller, and I'm also going to put an alpha edge, which is a little bit smaller, and another alpha edge a little bit smaller there. And here at this edge, at this vertex, I'm going to do the same kind of thing. Another beta edge coming in, an alpha going out, an alpha coming in. Up here, we need a beta edge in that direction, a beta edge coming in, another alpha edge going out. And down here, same story. Beta, beta, and another alpha coming in. Okay, now I'm just going to repeat this. Okay, I'm going to repeat this. At no point am I going to join one of the existing vertices to another existing vertex. Because if I do that, I will introduce a loop. And I want to make sure that this space has no loops. Okay, so I'm never going to connect any vertex to an existing vertex. I'm always going to just be creating new vertices. You know, I'm going to keep going in all directions, just keep on adding vertices and adding edges, never joining up to what we've already had. So at this point here, for example, I have to create three new edges. I have to create a new beta edge, a new alpha edge, and another alpha edge coming in. And then at this point, I need two new beta edges and another alpha edge. And then, so I get this kind of, I get what graph theorists call an infinite, regular, ternary tree. So this is a regular, infinite, ternary tree. it's some kind of analog of like a binary tree where you have something like this, and then at each node you have two more going out. I guess to make this thing, we also need to go in this direction to make it completely regular. Okay, so that's kind of like a binary kind of tree, perhaps. And this is sort of a ternary tree. So at every vertex, there's got to be four things coming in, four edges coming in, and we just carry on at every stage, creating three new edges going out, and labeling them all betas in this direction and alphas in this direction. So this is some big infinite graph, X, which is a covering of B. And it's a particular covering. It has the property that it has no loops. Because it has no loops, it's called the universal covering. And in some sense, which we'll see next time, it kind of covers all the other coverings. So if we try to understand all the coverings of this modest graph B, all the coverings of B turn out to be what are sometimes called two-oriented graphs. And these can be obtained in a very general way. So this is so start with any graph, let's say a finite graph. Start with a finite graph with four edges coming in, or edge arms, maybe I should say. They don't have to necessarily be separate edges, edge arms, coming into any vertex. So for example, suppose we have, let's say, three vertices, and we have four arms coming into this one, four arms coming into this one, four arms coming into this one. And otherwise the graph can be rather arbitrary. So let's just randomly connect these things. Okay, so there's a graph, all of whose vertices are of degree 4. Just a graph, all of whose vertices are of degree 4. Okay, the claim this graph can be two-oriented. And that means, i.e., we can label the edges alphas and betas so that so there are two alphas and two betas at each vertex. And we can label them in a directed way with one in each direction. So how do we see that? So the proof relies on a classical, relatively elementary result of graph theory, which is the presence of an Eulerian circuit. So an Euler path is a path on a graph that visits every edge once. And an Eulerian circuit is a circuit that starts and ends at the same point, which passes along every edge exactly once. And Eulerian circuits exist as long as all the edges are of even degree, which we have here. So we can easily make an Eulerian circuit. Let's do that. And making an Eulerian circuit is easy. You just make random choices at every stage, and you have no thinking is involved. So let's start here, and let's go like this. So we'll go here first, and then maybe we'll go here. Every time we enter a vertex, we have to leave it. So maybe we'll go in this direction. Okay, so maybe this is 1, and then this is 2, and then this is 3, and then this is 4, and then we have to leave. Go down here, so that's 5, and then here, that was 6. So we've gone along every edge exactly once. How many edges are in the Eulerian path? Well, the number of edges in a graph is related to the sum of the degrees of the vertices. Okay, so if the sum of the degrees of the vertices is always twice the number of edges. Okay, so there are in this case 4 times 3 degree. The total degree is 12 because here's degree 4, degree 4, degree 4, so degree 12 altogether. And that means that the number of edges will be 6. In particular, the number of edges is even. So we're dividing a multiple of 4 by 2, which gives us an even number of edges. Okay. That means that we can label this Eulerian circuit that we've just found has an even number of edges. That means we can label them alternately alpha and beta. All right, let's do that. So the first one was alpha, and we won't give it a direction yet. The first one is alpha, then the second one is beta. The third one is an alpha. The fourth one is a beta. The fifth one was in this direction. The fifth one was alpha again, and then finally a beta. And then we're back to where we started. So we've gone alpha, beta, alpha, beta, alpha, beta. And that ensures that at every vertex now, we've got 2 alpha edges meeting there and 2 beta edges meeting. That's the condition that we want to have. But we still need to orient these edges. How do we orient the edges? Well, we look at, say, the alpha edges. So look at just the alpha edges. Here's an alpha edge. There's one coming in and there's one going out. So the alpha edges will themselves form some circuits. Maybe more than one. There might be a circuit of alpha edges here, and there's another circuit of alpha edges there, and so on. So there's a circuit of alpha edges. We're going to label them all in the same direction. We're going to make a direction for all the alpha edges so that we're going around the circuit in the same direction. So we'll arbitrarily say we're going that direction in alpha, that direction alpha, and that direction alpha. And that will ensure that at any vertex, there's one alpha going out and one alpha going in. We'll do that same thing with the beta edges. The beta edges also form a circuit. There's the circuit of beta edges. And so we'll just choose an orientation for that circuit. Say that direction there, and then that direction there, and then that direction there. And then that also guarantees that the beta edges have the property that there's one going in and one going out at every vertex. So conclusion, we've sort of justified this claim that all what you need to do is to start with a graph, all of whose vertices are of degree 4, and then we can label the edges with alphas and betas so that there are an incoming alpha and an outcoming alpha and an incoming beta and an outcoming beta at every vertex. In other words, that graph is then a covering of B. That's the essential covering property that ensures that that graph is going to cover B. So this is then this X is a covering of B, which is our wedge of circles. All right, so next time we're going to have now a look at how the fundamental groups of covering spaces relate. Things get quite interesting, that there's a very nice connection between the fundamental group of a base space and the fundamental group of the covering space. And it turns out that somehow mysteriously this connection is intimately analogous to Galois theory, the theory of Galois theory of fields. So what's going to happen here is very similar to Galois theory. It's a sort of interesting and mysterious thing. So we'll see you then.